So for the second part here, I wrote prior and posterior distributions for mean and standard deviation. So just a heads up for mean and standard deviation. So we have the mu and sigma. So what we're going to do is we're still going to try to keep things a little bit simple in a sense that earlier we know that normal mu sigma, if I have yi, or I should say y1 through yn, iid. So the normal density does have two unknown parameters, right? Both of them can be random, but to keep things simple to start with, we're gonna first of all work with mu to be random and then sigma to be known, okay? And then we're gonna move to the other case where mu is fixed, but then sigma is random, okay? So we want to keep it simple in a way that we still work with what we call one parameter model. Okay, so I'm gonna write it down here, one parameter model. So we have seen one parameter model before. The beta binomial conjugacy that we saw before, if you remember, the likelihood was LP is this, see. It's from a binomial experiment, right? And then that's a one parameter model because the only unknown is P, okay? N is fixed and Y will be given once we observe the data, okay? So what we're doing here is to start simple. To keep working with one parameter model, we're gonna, like I said, first of all, mu unknown, but sigma is known. We're gonna see how we can derive, or like I would say, like design a prior distribution and then go to the posterior. Okay. So that's for the first one. Pretty exciting, as you can tell. The second one is mu gonna be known, and sigma is unknown. Okay, so we're gonna see how that works. So, so for both of the two cases, we're gonna look at how to specify a prior for the unknown, work with the likelihood function, and then derive the posterior. Okay, so today it might be a lot of deriving, so just be prepared. And so we're gonna start with the first case in a minute. From last time, we know that we need to have prior, likelihood / data, and then to the posterior. And we know for the beta case, beta binomial, that's the conjugate beta priors that we have seen. Okay, so the update becomes pretty straightforward. As long as you know the beta prior and the likelihood function. So some questions that you might be wondering is, well, I already told you that we're going to work with the normal sampling model. Okay, so that's how the data are going to be behaving. So what we're going to do with the two parameters, mu and sigma, I also told you that we're going to keep one as fixed, the other one as unknown to start simple. But then, of course, the question will be, well, what if I assume sigma is known, mu is unknown? How can we specify prior? Okay, and then also, are there conjugate priors out there that we can actually get to the particular known analytical solution of the posterior? Okay, so keep those questions in mind because that's the key. All right, so for the prior distribution, before fixing one and letting the other one as unknown, when you have two unknown parameters here, we can actually write the likelihood in terms of the two unknown parameters. Okay, so this is the basic setup here. And you always try to use the capital L and then put the unknown parameter in the form for it. So if I'm going to let both of them to be unknown, then naturally you might be thinking, okay, I will probably need a joint prior distribution. We don't know what it is now, but because both of them are unknown, this is what you typically would do, right? Like mu is unknown, sigma is unknown. We try to incorporate prior idea or prior information into this, then we should probably give a joint prior. And then we can use Bayes' rule to get the joint posterior. So notice the notation here. You start with likelihood, both of them unknown here. Joint prior, right now we don't know what they are, but just we have to write it carefully and then correctly. And then the joint posterior is the conditional distribution of mu and sigma together given the data. Okay? So this is the general setup And now we're gonna make sure that we can get you the first situation that only the mean is unknown and sigma is known. So it's a little lot of stuff going on here. And so first of all, because there's only one unknown parameter, we're going to start to assume sigma is known. So the first step, as you might be guessing, is that the likelihood function is no longer is no longer a function of sigma. Okay, sigma is known. And if you think about the prior, what we're going to do is whatever is known is going to be thrown into the conditional sign. Okay, so for now, we put conditional and sigma there. So that will be the prior. And you can see the similarity as what we were writing before. Now it is going to be a posterior distribution for mu, and we always condition on sigma. So get yourself familiar and the practice of moving things, like moving terms, like in the joint distribution or in the conditional distribution, and get to the point that you know if it's something is known, you put it after the conditional sign. If it's the random variable that you're working with or random parameter you work with, then you focus that. Okay. All right, so that's the flow, I would say, like roadmap of what we should do. So now we're going to do it step by step. All right, so the prior distribution, which actually will become a conjugate prior, as we will see in a minute, it's going to be another normal distribution. Okay, so get the idea across. There are two normals going on here. One is the sampling model, which is what we assume in the beginning, that the data is going to be IID normal. Okay, so that's the normal at the sampling data model. Okay, that's for the data. What I'm talking about now is the prior distribution for mu. And what I'm saying is, if you're going to start with the normal prior distribution for mu, when sigma is known, you combine with the sampling density, which is the normal as well. You're going to go, because it's conjugate prior. We know that by definition, conjugate priors are the prior distributions that you can come to the posterior distribution, both of them coming from the same family. Okay? So that means if you start with the prior, normal prior for mu, it's conjugate. You're going to come to a posterior distribution, which is also a normal, okay, for mu. Okay? We don't know what it is now, and once I show you, you might think, oh, this looks crazy, but you can actually derive it, and that's what we're going to focus after I talk about the basic information here. So conjugate prior goes to the conjugate posterior in a sense that, well, mu, given the data, right, that's in the posterior statement, right? And also, so now we're using a new notation, phi. I'm going to talk about this in a minute. This is a variable transformation, which is what I talked about in the introduction review as well, that a lot of times it's probably easier working with the precision, which is defined to be 1 over variance. Okay? So this is just another way to talk about the spread, okay? The different parameter here. So I'm using it mostly because it's going to be easier to see when we are trying to derive what the posterior distribution, what the normal should be. So right now it looks a little bit crazy, don't worry. But I do want to show you that what this phi is. And of course, we also define phi 0 because that's the precision for the prior sigma 0. Okay? So you have phi is the precision from the data model. Okay? And then you have phi 0 is the precision coming from the prior. And by definition, it's 1 over variance. Okay? So suppose we take what's written in equation 10 for now, that this is the posterior distribution. So that means if I start with this prior, I combine with my data, I'm going to come to a normal posterior distribution for mu that I can start making inference about. Right? So remember, in previous unit that we're talking about beta conjugate prior for the binomial likelihood, right? Then we come to another beta distribution, and then all of the exercises that we did last time is talking about, well, I know exactly what the posterior distribution is. I can do all kinds of summaries about it. Okay? So if you know what the posterior distribution is, you can do that pretty easily, either through the exact method, like so what is it, beta area function, right? Also like beta interval, or use p beta, q beta, that kind of functions can get you there. Or through simulation, which is like doing R beta. You take a large number of draws and then summary based on that as approximation. So you can pretty much imagine now, if we're going to work with this posterior normal distribution, if I know all of those quantities, p0, mu0, n, and y bar, and phi, if I know all of this based on my equation 10, I know everything about this normal distribution, right? And each of this is what? p0 is from the prior, you specify the value, right? mu0 is also from the prior, you specify the value. N is from the data, it's the sample size, it's given, right? And y bar, like I said earlier, we're gonna see how to simplify this. You don't need to know each of the value itself from the data, but just the mean, okay? And lastly, phi, okay? Phi at this moment is assumed to be known. Okay, so keep this in mind. The form, and I guess right now looks a little bit daunting, but next 10 to 15 minutes is going to be devoted to how to derive this. Okay? So deriving this, it's not too bad. So let me just set it up for you, and then we're going to work through it slowly. So remember, when we are trying to deal with any kind of derivation of the posterior, what we do is we start with the prior, right? And the prior is what? Is mu. And it's mu given phi, or like sigma. So right now we're going to start with phi, right? So what we have is we know this is what? This is a normal distribution, right? So we can actually start to write out the entire density of this normal. Let me just get it up for you. If you do that, going to be 1 over, yeah, so let me start with sigma first, so it's less confusing. So sigma here. So what do we have? We have 1 over 2 pi sigma 0 squared. So again, let me just write it here. Mu given sigma is normal. We use mu 0 and sigma 0, right? That's the prior that we use. So in order to supply the detail, we're just going to write out the normal density here. So it's going to be exponent negative mu minus mu 0 squared, and then 2 sigma 0 squared. Right? That's just writing normal density. Okay? What I want you to do now, starting from now, is instead of working with sigma, let's work with phi. And then that means this is going to be related to phi as well. So I'm just going to write out the density for you. Nothing too complicated, just because phi is 1 over sigma squared. So pretty much you just replace sigma 0 squared here with phi 0. Okay, so one thing is you have to bring it up. It's not in the denominator anymore because it's 1 over sigma squared. So let me write notation. This is your relationship. Okay? So we replace that, okay, using phi 0. All right, so that's from the prior. And we can also now writing about the posterior, the likelihood. I'm going to do on the board, but you can just try it yourself, and then we're going to look at it together. I just correct one thing. I think I should just write equation equality here instead of proportional sign. It is the exact PDF. You can write for yourself. I'm just going to write the joint density here. So in the first line, I always first write with sigma, but then we're gonna move to phi. Just want to show you the steps here. So phi is 1 over sigma. If we do that, then it becomes and one more step I would do it for you is we can simplify this joint density, which is the likelihood, and we did that in class as well as in homework once. So basically have n copies of 1 over square root of 2 pi, raise that to the power n. And for phi, you have n copies of that as well, so that goes into the power n over 2. Okay. And in the exponent, it will become the sum of all of the yi minus mu squared. Okay. All right, so now the task is for you to derive the posterior. And we know that posterior, so given the y, so y1 to yn, and then sigma, or phi, let me write sigma, just to be consistent with before. It's going to be proportional to a base rule to the prior times the likelihood. So again, you can work with the proportional sign. So anything that's not about mu can go into the proportional sign. Okay? Just so, for example, what you can do is, well, those 1 over 2 pi's, they're going to be constant, right? So they can go into the proportional sign. Actually, phi0 raised to the power 1 over 2, that's constant as well in terms of mu. Okay, right now, we only care about random parameter mu, so everything else not about it is going to be a constant. So those will be constants. This, unfortunately, cannot be thrown away because mu is involved, right? And this can be thrown away, as you can tell. This as well. This cannot either, okay? There's mu here. So focus on the 2 terms, I would say, in the exponent. And then try to simplify as much as you can. I'm just going to write the result, which is shown earlier on the other slide for you, so you can see if you can get it step by step. So the final posterior we know should be, I'm going to write phi here. It's going to be normal. Plus y bar. That's the mean. And then the standard deviation is this. Yeah, so take your time. It's going to be some simplification and then combining terms when you're working with this 2 exponent function. And one more thing is, just like what we did before, when we're trying to recognize the beta distribution, remember the beta posterior that we're trying to try to recognize, we focus on what's in the power, right? Because we know that a beta function, or sorry, a beta density should have p to some power minus 1, right? And then 1 minus p to some other power minus 1. So those are the 2 shape parameters. Okay? Normal distribution, we know the density, well, this is just an example. This is the normal density here. That should have this kind of general form, right? You should have what's in the exponent function. This will be its precision, right? and then whatever you can do here will be its mean. Okay? So for you to recognize what the final normal posterior is, you have to work it out, simplify it to such extent that you'll be able to recognize the mean and the precision directly from what you can see. So take your time. Oh, go ahead.
Do you want us to find the exact PDF or what it's proportional to?
Yeah, only proportional to. Yeah, so you don't need to worry about. So that's why I was saying that those are constants. Those can be thrown away into the proportional sign. But you focused on the mean and variance or standard deviation and precision. So take your time. I'm just going to walk around and help with any particular question. So what is y bar? Y bar will be the mean of all of the y's. Okay, so that's why I was saying, well, you see that now we have a sum of this, right? So when you do a little bit more simplification, yeah, you might try to put it into y bar. So what you can do is sum of all of the yi's will be n times y bar. Okay, and you actually see the form here. So it's getting, yeah. There are certain tricks, so take your time to think about it. I will just jump in whenever I think people are ready to look at things for further simplification. So you keep working on it. I will slowly start writing up some of the steps.
Yeah, right. I'm looking at that. There's got to be something you can do there somehow. It's not the same thing as sum of yi times sum of y. It's not the same thing. It's not. Wouldn't it be like?
Okay, last time we had to use the property of the new.
Oh. I mean, I feel like we should look at the end result. If I were smart. Look at that leverage. Right. Yeah.
You will have to throw out everything because it's proportional because it's leave this out because that's mine.
I put it with the 1/2. Yeah.
I don't think you want to because the final form should have that.
Yeah. That's the next step.
Okay, so up to this point, what I did is simply just expanding those square terms. But we can start to see certain things can be thrown away into the proportional sign. Okay? So first of all, the only random variable here or random parameter here is mu, so anything not about mu can be thrown away. So we already did those two constants, I mean, in front of the like the square root of 2 pi, that kind of stuff. So that's the first step. And once we get to here, so you see that we have this mu 0 square. So that is not about mu. Okay, so that can go away. You can just cross it out, it's fine. There's that. And also the pretty nasty term, sum of all of the yi squared, that's also not about mu. Okay, so that goes away immediately as well. So what you're left with And this is where we can start to see that you can, instead of writing sum of yi, you can write it as the product of n and y bar, like what Kobe asked earlier. Okay, so this is the place that you can do 2 mu and then n y bar, because sum of the yi is n y bar. And then lastly, you still have this term. So one more hint for you, and then we're gonna pause for a little bit for you to work on, is now we have terms about mu squared, 2 of them, right? And then also just mu times something, 2 of them. So we know that we need to combine them in some way, right? And eventually, we were told that it's gonna be a normal posterior distribution, so you will know that you will try to recognize in a particular form that in the exponent, what you're gonna see is you're trying to have, I'll write it directly here. I'm just gonna use capital A here, and then mu minus capital B squared. So this is what we call like a kernel of a particular distribution. Okay? So if you just focus on this, if you can recognize what A is and what B is, you have to rearrange terms, of course, but the A will just become the position, and B will become the mean. So the goal is you should simplify what we have from the last step here into a form like this, that you will be able to recognize B and A. From there, you will know exactly what the posterior normal should be. Okay? We already covered what it should be, so hopefully you can match it after a few more steps of simplification. I will start writing slowly, so take your time. It's just going to take time for me to write anyway. So notice that I keep the -1/2 out because we want that to be separated, because we want to see a form like this. So I have this -1/2 out, and I have some constant actually multiplied with mu squared, and then minus some constant 2. I think there's a 2 in front of this times mu. Okay. The last step will be completing the square. So just so you know, completing square, if you have a x squared plus bx, it's gonna be a x minus b over a, 2a actually, squared, right? With some extra term. So the thing is here, the extra term gonna be a constant, right? It's gonna be considered as a constant because we're working with proportional sum. So you don't even need to worry about you added some extra term there. So this is the general form for you. And the last step will be recognizing the connection of the final form to this thing in the blue box here. All right, so you're gonna try to recognize A and B from this form here. We know that A will actually just be the sum of P0 and N times P, right? Based on the form that we see here. So A will be P0 plus N times P. And then B will actually just be the ratio of what's in, I would just say what's in the second parenthesis over the first parenthesis, right? So I'm just going to write it out. So we know because of completing a square, say ax squared plus bx, you pull the a out, and then you account for the fact that you put out the a, so you're going to have b over 2a here. Because we already have a 2 here, so you just directly have phi0 mu 0 plus n plus phi n y bar over phi0 plus n. Okay, yeah, so yeah, take your time. I mean, after class in particular, trying to figure out like the steps, and after today I will upload detailed derivation notes as well on Moodle, so you can use that as a study guide. And before we move on to the case that I was saying, now this is mu is unknown, speed is given, and we're going to work the other way next, just to get the practice. You'll see how things work in action. But before we get there, I do want to just spend a couple of minutes just looking at the form a little bit more closely. That we know this is going to be the mean, and this is going to be the standard deviation of the posterior, right? So if you look at the mean a little bit, remember for the beta binomial conjugate case that we saw before, that we showed that the posterior mean is a weighted average of the prior mean and the sample mean. Okay? And that's how we can see that the posterior is really trying to put together the prior and the data and then come to a compromise or like a composite result. So can you see that here as well? Y bar is the sample mean. Okay. Mu 0 is the prior mean. Right? Mu 0 is here. That's in the prior. Do you start to see that a little bit? Do you think of this as the total weight? What you can do? So that's why you can probably start to recognize why we want to write the mean in this way. That if I try to break this into, let's see. Let me just start with the whiteboard. That's easier to read, I guess. So we have the posterior mean in this form. Okay. And if you break it into two parts, you can see that you're having phi 0 over phi 0 plus phi n mu 0 plus phi n over phi 0 plus phi n y bar, right? So what do you see here? You see the prior mean multiply with a prior weight, and then you see a sample mean multiply with another weight, right? And the two weights add up to 1. Okay. So just pause here for a little bit, especially thinking about the effect of n, because again, n is the sample size, right? We know that in a Bayesian inference. So in the introduction class, we talked about good prior helps, bad prior hurts, but then if you have large enough sample size, the prior is going to matter less and less, right? So we saw that, I think, in the beta binomial when we're thinking about the A plus B, the two shape parameters, the sum of them is the prior sample size, right? Here, the effect is on the phi, right? Phi 0 is the precision of the prior, and phi is the precision of the sampling model. So if you focus on n here, if phi and phi 0 are fixed, then larger the n, the bigger the weight of the y bar, right? So that tells us if we have a larger sample size, well, we have to assume that y bar is the same, but regardless, just think about the effect of n itself, that if n is larger, then the weight from y bar are going to be more like bigger in terms of their effect on the prior, on the posterior mean, I should say. Make sense? Yeah, so keep that in mind. A lot of times, well, for simple models like this, we can see the effect pretty clearly. Later on will be less, but overall, the posterior will always be something between the prior and the sample. And we need to see, say in this case, it's nice to see that the effect of n is on the overall posterior mean. Okay. Another thing interesting to see is looking at the precision itself. So we know that, so we know that B 0 plus Bn times n. So this is the posterior precision, right? So phi 0 is the prior precision, phi is the data precision, and then we show that the sum of these two, phi multiplies with n, will be the posterior precision. Okay? So the implication here is that, remember, precision is 1 over the variance, right? So what this tells us is that the posterior precision is bigger than the prior precision, right? It is also bigger than the data precision. Okay? So if you have precision being bigger, you're having smaller variance, right? So that's why overall later when we start to like really generate draws and then plot things together, you can start to see what we saw before in the beta binomial as well, that you start with the prior distribution with the bigger spread, meaning more uncertainty. But then when you go to the posterior, because the data helps you to sharpen your belief, you're going to have a shorter or smaller spread over there, less uncertainty. Okay? So it is nice to see in the normal case because we know exactly what the standard deviation is evaluating, right? It's measuring. For the beta binomial, it's a little less, but we saw it on the plot. But here we can see mathematically why that makes sense. So keep those in mind. Those are all features of Bayesian inference. Later on, in more complicated models, it's less obvious to see them, but they're always happening behind the scenes. Okay. Make sense? All right, so hopefully everybody feels super comfortable now with all of the derivations. So let's go to just quickly about how you can simulate posterior draws of things. I won't go into detail of how like you write all of the code, but it's strictly following all of the formula that we derived. Okay, the expression for the for the mean and the standard deviation. These are the two for the posterior mean and posterior standard deviation. So I basically just plug in using R so we can compute it. Okay, and then in the end, we draw 1,000 draws from the posterior normal distribution and then plot it. So what we did here is we just plot it together. Okay, yeah. So this just sample code. Maybe later you're gonna find them useful. All right. So now is the time for us to do the other case, and we'll leave it to you to practice more. This is the case that sigma is unknown, the mu is known. Okay? So everything still follows very similarly. And starting from equation 11, we start to focus only on sigma, okay, not on mu. And mu is given. Okay, so mu is known. So the likelihood function is the function of sigma. The prior distribution is for sigma. Mu is given, so it goes after the after the conditional sign. And then the Bayes rule going to help us to get a posterior for sigma, given the data and the mu. So see the similarity, it's very similar to what we did before, but we're switching places of sigma and mu. So I'm going to tell you here is that we actually have a conjugate prior for 1 over sigma squared, which is for the phi. That's what you see here. So it is a conjugate, and it's a gamma distribution. I'm going to give you the density in a minute. But overall, if you have 1 over sigma squared, which is phi, is a gamma alpha beta. Just keep the note for now. I will show you the density. Then if you combine that with the sampling density equation 15, that's what we see before, you're going to come to another gamma distribution with this updated parameter. Okay. And also, just so you know, if you know all of those terms, we know, so alpha and beta, they're coming from the prior. So you have the values for them, okay? And n is the sample size. And you can see here that you will be able to get from the data as well, because all you need is each of the yi. Okay, and mu is given. So that means if you have the set of known quantities, you're able to simulate or using any other like P gamma, Q gamma to summarize the posterior distribution. Okay, so I'm gonna write out the gamma density for you, and then for the rest of today's class, just spend the time, work through how you can make the derivation yourself. The textbook covers all of them, so feel free to read them as well. But like I said, after class, I will upload the derivation notes so you can work with them as well. So let me find the correct gamma density for you. I just want to start with a whiteboard so it's easier. So the prior for 1 over sigma squared is a gamma. So we know 1 over sigma squared is gamma. So by the way, gamma is a proper density. It's for a positive random variable. Okay, so that's why typically, so for precision, which is 1 over variance, it's going to always be positive. So that's why it's typically using the gamma distribution to model that. So the gamma density will be beta to the power of alpha over gamma function alpha. Don't worry about it. They're constant. I just want to write the entire form for you. And then 1 over sigma squared to the power of alpha minus 1. And then negative beta times 1 over sigma squared. Okay. So that's the gamma density. So because we're working with 1 over sigma squared, so the random variable is 1 over sigma squared. Okay. And the likelihood, as we know, let me write L. Now it's 1 over sigma squared. It's going to be product. Yeah, you can work on your own. You don't have to follow my notes. I'm just trying to show you the steps. So the goal is to derive the posterior. Keep in mind that mu is known. So it goes after the proportional sign. So anything not about 1 over sigma squared is a constant. So that can help you simplify things, I think. I added the final result for you because it was from the previous slide. Maybe you didn't get the chance to write it down, but the final goal should be recognizing this to be a gamma with alpha plus n, and then beta plus the sum of the squared difference from each observation to the mean. Cheshire pointed out, I think there should be a 1/2 here. Probably missed it. Should be correct. Yeah, the first is alpha plus n. Yeah, it's not 2, sorry. So I typically write alpha like this and 2 like this. Just so you know. I don't think we'll have time to finish at least for me writing the last minute, so we're just gonna end, or like you can work on this, and then when we come back on Tuesday, we'll finish the final derivation, and I will recommend you to bring your laptop next Tuesday because we can do the lab too.